Hey there, I'm back with another Vulkan demo. This is a slight recreation of my last demo with a entirely new system under the hood. So previously, um, everything from start to finish with the entire Vulkan renderer was very hard-coded to do a very specific task, and that was to render those 200,000 cubes. This is not 200,000 cubes you're looking at right now. This is 100,000 cubes. Because what I've been working on the past week is an entity system, and this entity system can do a lot of other cool things that is much more dynamic and can do a lot of things that are actually useful, but also greatly increase the bandwidth requirements. So running this with 200,000 cubes and OBS at the same time on my fairly old R7 360, which was low-end 2015 hardware, is no longer quite as reasonable to expect it to do. So as I mentioned, this is running atop a new entity system, which means that every single one of these cubes can be added or removed at runtime independently of the others. Like I said earlier, the original demo, everything was very static and very hard-coded. That is no longer the case. If I exit the application and I quickly jump over to another set changes, and I rebuild my shaders, I rebuild. This is a very small modification to the application you just saw, to show off the dynamicism of this new entity system, and then we'll go into some details. So if I left-click at any point, it creates a cube. Every time I click, it creates a cube in a random location within a specific cubic area. Look at them cubes go. Every time I click, creates a cube. Entities can be added at any point during runtime. If I right-click, I get a monkey. Look at that. Look at those Suzannes all showing up. If I middle-click, it deletes. Every time I middle-click, it deletes an entity. Ooh, look at them go. Ooh. It's randomly selecting an entity. So it's not based on the order in which they arrived. So I can look at all those entities. Woo, and then delete them all. And then add some more. And then delete them. And then add some more of another type. Look at all those monkeys. So yeah, this, I can dynamically add and remove entities at runtime, and this is all handled in a way that's extremely efficient for the CPU and GPU to handle. And let's talk a bit about what that entails and the requirements for the system. But first, let's look at how this is being done. So here's all the logic for the demo you just saw. Every time we get a mouse down button, a mouse button down within a specific range, we create a vec3 translation, so a position within that range. So this is actually a 20 by 20 by 20 cubic space centered on the origin. And then we say if it's the left mouse button, then we create an entity with a cube at that position. If it's the right mouse button, we create a monkey at that position. Otherwise, if it's a middle mouse button and we have entities, remove it. Now this is fairly high level, but the GPU doesn't see this. The GPU doesn't see anything like this, because the way the GPU works, if we actually go in here and look, the GPU loves this. This is the draw command I'm using to render all my meshes. Now the way this works is this is a form of instanced rendering, which is where instead of saying here draw a cube here, and then draw a cube here, and then draw a cube here, and then draw a cube here, you say draw 4 cubes, and then the vertex shader can say I'm the nth cube, go look up its data from another buffer somewhere, and then offset itself into the correct position in 3D space. So what that means is, if you have a whole buttload of entities, and they'll have different models, you want to group them by model. So that means you have one of these commands per model type in your scene, and no more. But, as we just saw, we want to be able to just shove cubes and monkeys into the scene together and then just remove an entity and not care which model type it is. So that means we need abstraction. Specifically, the entity system. If we go look at the entity system, is based around this model ID. And this model ID is an enum which can represent each of the different models that I have loaded. Now this is a list that I have to update manually, which is fine. And these models are loaded here in main, right here with this new thing called a model buffer. The way model data is handled in 3D applications is that you have vertex data and you have index data. Because if a face shares an edge with another face, then that means those two vertices are duplicated between those two faces. So to avoid having a massive explosion of vertex data, just like way more vertex data than you probably want, what you have instead is you have all of your vertexes in one buffer, and then you have a buffer of indexes into the vertex data. So instead of having all of those 3 float vectors be duplicated, you have, say, in my case, a 32-bit unsigned integer being duplicated. So this model buffer is responsible for loading a set of models, and the models are within here. Here's one model being loaded, our cube, and here's our monkey. And this data gets shoved into a common vertex and index buffers, so that all of the model information is just in a single vertex buffer and a single index buffer, instead of a whole 2 buffers per model. And that includes rewriting index data to point to the correct offsets as each model gets pushed onto the end of this buffer. And you can see here I'm loading this cube and I'm including it in the actual executable, and I'm telling it that this is a cube, and here I'm loading the monkey, I'm telling it the monkey, and this is just a small macro that just includes the obj file as a string, and then calls. So this embeds the obj model in the executable, and then calls my obj loader, and then can error out if need be, and assigns it to the correct model ID. So now that we have model IDs, these model IDs are actually, each model ID is actually a byte. If I can pop over here, it's actually a byte. These are not rich enums, these are not subtypes. These are just straight C-style enums, which means we can turn these into their integer variants. And that's exactly what the entity system does. So we have this array. The entity system has an array that's grouped by model. Each entry is this type called grouped entities. We'll look at that in a moment. And then there's enough of these grouped entities so that there's one for each type of model. And this is just a little const function that just says, here's the last thing, turn it to a usize, and then add 1. So we have the correct number of lengths so that every single model enum entry is a valid index into this array. And then so up by model, and then once we have a grouped entities, we can look up by just straight index into our list of entities. And this is cool because if we want to remove an entity, we don't want to reshuffle the entities that are past it in the array. So we also track holes. This can be done more efficiently. This is a first pass, which is a list of all indexes that currently do not have a entity. So this means that I can remove an entity from this list. There's still valid entity data in that index, but we've marked it as not being used. And the next entity in that model type that gets added to this entity list will go there first. And This means that we don't like grow massively, and indexes into this remain stable. And it's fairly small amount of logic for that. And this whole system works upon this struct here, an entity index, which contains your model ID and then your subindex. So this is a unique, well, it's not unique for the whole lifetime of the program, but it's unique for the lifetime of the entity it's referring to. This is the ID or index into the whole entity system as a whole to say this is the specific entity I want to refer to. So we come back over here to our main, and we go to where we were doing the mouse buttons. You can see when I push a descriptor, because the entity itself does not know what model it is. So that means we need a separate type to pass in here that can contain the model ID, and then this data gets stripped out and put in the actual entity. So when we push that, the entity system goes and puts that newly created entity into the entity system, and all is good. But it returns back one of those entity indexes. And so here I'm just pushing it into a list. And this list sticks around between frames. And that's that. And then that means that down here when I delete them, I just say, do I have any IDs still stored? Any indexes? And if so, give me one of them randomly. I'm just creating a random index into those IDs. And then I remove it, which also gives me it back. And then I say, entity system, here's an entity index. I don't especially need to care about which model type it is or where in the entity system it is. Just go remove it. And that's fine. That's it. So very, very clean outwards, outside perspective on how to interact with this, with the core details hidden away in a really nice little way that is efficient for the GPU, because these entities, if we go into our grouped entities, we can just upload this straight up. We can just upload the entity list. That's it. We just upload the entity list. And that's awesome because the entity just contains only the data it needs to know about. So right now that only is a 4x4 matrix, which embeds in it the position, rotation, and scale information. And then a U32, which represents whether or not it's a hole or not. So then the vertex shader can say, I know which instance of this mesh. Let me look up my data into this buffer. And this is the data that comes straight from this entity list. This entity list is exposed to the GPU shader right here. So it can retrieve itself and say, if I am not present, if I'm a hole, and then just puts all the vertexes at 0, 0. 0, 0, 0. So you don't get any fragments, and you don't have to spend any more time in the pipeline paying for that. There are other slightly potentially more efficient ways to do this, so that you don't have to upload data for any holes. But again, this is a first pass, and this is well more than efficient enough. This is not a finished system, specifically because this entity here, this is only going to ever contain the data that is common for all entities, which means it's probably never going to get more than this. Like, this is probably going to be like the only data that entity is ever going to have, probably, depending on the game project. I don't know, because I'm building this to be like a common core code base between game projects in the future. So layering on top of this is going to be another entity system where computers really do not like to when you have I have a big list of things and they all have a common interface, but I don't know what specific things they are, and I'm just going to call them. I'm going to iterate through them and call them, and they're going to figure out what to do. That is really, 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 really slow. It's horrible for a whole lot of reasons, primarily due to the cache and because of the branch predictor. So you have a bunch of virtual function calls. So now the CPU doesn't know where it's going to jump to prepare that ahead of time. And because they're all of different types, the CPU can't guess what values to load ahead of time. So tons of things that make that bad. So And then also they're all might be of different sizes, so now you have to either like handle the largest potential size or allocate them all individually, which is really expensive in its own way. So I'm going to layer on top of this another entity system where each type of entity, so say you might have a specific bad enemy A and an enemy B and an NPC C, and you have multiple of each in the scene. That above entity system is going to have a list of A, a list of B, and a list of C, and each of those are going to have their own separate data. So like maybe the enemy might track who it's attacking or its health and stuff like that. And then it contains an entity index. This entity index to say that this is my mesh in its position, and that corresponds to what gets uploaded to the GPU. And then that entity system can then be built to be able to iterate over all of those separate entity types individually, which is a lot faster, and perform their own logic, and then update this underlying entity data for the new positions if they change. I also need to build up a system for static unchanging data. So like entities that don't change position over the course of a level don't need to be uploaded every time, because this is 4 by 4 bytes each, so that is 64 bytes plus the 4 bytes for the presence, so that's 68 bytes per entity. So with the 200,000 cubes demo, which is not what you've seen 100,000 cubes with this entity system, but with 200,000 cubes, that's a lot of bytes. And if we do a little bit of math, that's how many kilobytes, and if we do a little bit more math, we're uploading almost 13. When I run this with 200,000 cubes, I'm uploading almost 13 megabytes of data to the GPU every frame, which explains why OBS does not like it, because OBS has to copy uncompressed video stream from the GPU to system memory every single frame it wants to capture, which is a lot of bandwidth in and of itself. So those two fight out, and they both lose, and you get choppy performance from the game, and then horrible OBS performance. But for that sort of situation, the data that's being uploaded doesn't need to change. And you can think of in an actual game situation, if you have model data, you have geometry data, so like your actual level itself, that gets loaded once, right? And then it's static mesh. And then say you have like a bunch of items in the world that are not baked into the scene scene geometry itself, but don't move past the initialization of the scene. Those things don't need to change, right? So those don't need to be uploaded every frame. So you need to build up an abstraction on top of this for those, so like they can like have a similar sort of like interface, so that like when I'm loading level data, however I end up structuring that, depending on what game project I end up forming this into, those can all those can be like pushed into that in an easy and robust way that's not prone to error, and then all be uploaded at once and be a lot cheaper, because over here in the renderer I have to do a bit of busy work to upload all that data, and this is where those 13 megabytes is being uploaded every frame. But you're never going to have 200,000 moving entities, and even if you did, because they're moving, you probably have to be doing CPU side logic anyway, which is a bad thing for that number anyway, even before the GPU becomes a problem. So that's my entity system. It's very fledgling. It's very incomplete. But I got interactivity. I got actual shaded models on the GPU that are interactive and dynamic based upon CPU side user interaction, which is really awesome. And I hope you enjoyed this video. See you around. Cheers.